So let's take a look at what we call simple linear regression. We call it simple. Linear you saw because the regression line is a straight line, but we call it simple because there's only one variable involved, and we'll do that first, and then we'll look at when more than one independent variable is involved. Okay, so here is a situation we looked at, and what we were looking at is a sample of low birth weight infants. So by low birth weight, it means they were born at less than 1,500 grams. The definition changes every now and again, but let's just say we use the less than 1,500 grams. And let's look at the head circumference. Now, what I'm going to be looking at is as a function of gestational age. So it's a little bit before what the WHO showed us. All right, so what we found, if we just look at all these kids, low birth weight kids, that the head circumference was pretty much normally distributed with a mean of 27 centimeters and a standard deviation of 2.5 centimeters. So, and they're approximately normal. So what this means is we could set up a 95% predictive interval, and here it is. It's 22.1 to 31.9, so roughly between 22 and 32 centimeters is going to be the head circumference. As I said, it's measured around here. So the head circumference of these babies, these low birth weight babies. So there is where we expect 95% of these babies to reside. Now, the question you might say to me is, can we do better than that? Can we bring in other information and get a better idea of, get a better predictive interval? And of course, we know from everything we've studied up to now that we get a better predictive interval if we have a smaller standard deviation. That's what regression is going to help us do. So, for example, suppose we have that if we look at 26-week gestational age, that the head circumference was, instead of the overall 27, is 24. And now these babies are going to be a little bit more homogeneous, and that's going to be reflected by the fact that the standard deviation of those babies is going to be 1.6. So I've slipped in a little bit of new notation for you here. Mu, I've put a subscript, of y given x, because we know x. So this is the mean of the y's for a given x. We know x, and we know x is 26 weeks. Here, the standard deviation is, we know x is 1.6 centimeters. Contrast that to the standard deviation overall of 2.5 centimeters. It's smaller. It should be, because these 26 weekers should be a little bit more homogeneous. They should be a little bit more comparable to each other than if we just threw them into a pool and we had 26 weekers, 27 weekers, 28 weekers, 30 weekers, whatever. All right? So we expect that there be a lot more homogeneity. Doesn't have to be, but we expect that. All right, what happens with 27 weekers? Well, for 29 weekers. Suppose for 29 weekers we observe that now the head circumference is a little bit more than the 24 centimeters. It's 26.5. It's not quite at the mean overall yet, but we get 26.5. Standard deviation, once again, it's smaller than this one, smaller than the 2.5, but it's at 1.6, which is the same as this. What happens with the 32 weekers? Well, suppose their mean is 29 centimeters and their standard deviation is 1.6 centimeters. All right? Suppose we had this situation. So if we look at them overall, we would say overall it's 27 centimeters mean and a standard deviation of 2.5 centimeters. But if we pay attention to the gestational age, we get slightly different answers. So here's what's going on. This is my attempt at freehand. So overall, this is the overall picture. We've got a normal distribution centered around 27 centimeters with a standard deviation of 2.5, and we did our predictive interval, which was from 22.1 to 31.9. So 95% of them are there. Now look what happens. If we go to the 26-weeker, now our mean is shifted down to 24 centimeters. Our standard deviation is smaller. So the blue curve here is tighter than that curve. So the blue curve is tighter than the black curve. But also, just like happened with the osteoporosis, it has shifted in such a way that up here on the black curve, we had about 2.5% of our observations are up there. Remember, 95% are between 22.1 and 31.9. That means 2.5% are up here. But if you take this down, you don't get anybody. None of the 26 weekers are going to be up there. You've missed them. You barely catch these guys. So this is what's happening. In each one, so here's the 26 weekers. I didn't put the 27 and the 28, otherwise this would just completely foul everything up. But here's the 26 weekers, here's the 29 weekers, here's the 32 weekers. Each one of these groups has their own normal distribution because each one of them is based on a large number of babies. The only thing they have in common, these 26 weekers, is that they're all 26 weeks old. But apart from that, the head circumferences are all going to be different. They're going to be varied. They're going to vary around with what mean. Around what mean will they vary? Well, the mean will be 24 there. It'll be 26.5 there. It'll be 29 there. And what standard deviation? The same, 1.6, 1.6, 1.6. Much more homogeneous than the 2.5. Let me repeat myself. And the mean, well, the mean is shifting. Now, if these are all done to scale, what I'm saying is if we have linear regression, if these means lie on a straight line. That's what linear regression is. That the means, when you join up the means, they line up in a straight line. Now, here's the scoop. Two very interesting relationships with the correlation coefficient. First of all, if this is our real regression line, all right, so this might be the 26 weekers, this might be the 29 weekers, and so on. And so here's the mean of the 26 weekers, here's the mean of the 29, there's our regression line. If that is the real regression line, and x and y are normally distributed, then here is the relationship between the two variances. Now, what are these two variances? Well, this is the standard deviation of the y's if we ignore gestational age, and this is the standard deviation of the y's if we bring into account the gestational ages. Square that and you get your variances. So here's the relationship. The variance when you bring x into the picture is equal to the variance when you ignore x multiplied by 1 minus rho squared. Rho is the correlation coefficient, 1 minus, which is between minus 1 and 1, so rho squared is between minus 1 and 1, so 1 minus rho squared is less than 1. It's between 0 and 1. All right, so here's the diminution. So your variance, or take the square root and you get standard deviation. So the standard deviation of these curves, when you take x into account, okay, these curves, the standard deviation of those curves are related to the standard deviation of the curve that ignores them by this relationship. So immediately when we think of correlation, we think of, oh, minus 1, 1, and 0. Those are the three correlations we looked at that were the interesting ones. Well, if the correlation is equal to 1, either plus or minus 1, then this variance here is 0, because 1 minus rho squared is equal to 0. All right? So what this is saying is there's no variability. If x and y are perfectly correlated, then knowing x tells us exactly what y is. All right? So there's no variability. That makes a lot of sense. The other one that's appealing is when rho is equal to 0. when rho is equal to 0, this is telling us that those two variances are the same. So knowing x or not knowing x, it doesn't help us in our prediction. It doesn't make it any more homogeneous. It's the same variance. So this is the variance interpretation or standard deviation interpretation of the impact that the correlation coefficient has on the regression line. And this is why I gave you that tip. You remember I said go off to the site and do the four, match up the four dot patterns with the four correlations that they give you. And I said to you, remember, I said look for the tightness. This is why. So if rho is close to 1, this is going to be small. If rho is close to 1, this is going to be small. So they're going to be they're going to be tight. The pattern is going to be very tight. So that's how you cheat in that game. Well, you don't cheat, you learn. That's how you learn in that game. So here is interpretation 1 of the correlation coefficient. It's the reduction in the variance or standard deviation of your conditional standard deviation or variance. There it is. Now you're going to see when we get to regression output, this is sometimes estimated by, the rho squared is estimated by something that's called r squared. So you're going to be seeing r squared. When you see r squared, and I'll point it out to you, when you see that, remember this equation, because this is what we'll be talking about. I mean, this is the result we'll be referring to. Okay, so this is the variance. Here's an example. So in our, we could work backwards too, because in our example, we had that the overall standard deviation was 2.5, whereas the standard deviation in the conditional ones, when we brought x into the picture, was 1.6. So if we solve this equation, we see that it's going to give us something in terms of rho squared. It's going to give us that rho is either plus or minus 0.768. How we decide whether it's plus or whether it's minus, we have to look and see whether whether y tends to increase with x, and if it does, then this is going to be a positive correlation. So we just look at the scatter plot. Now remember this, also this one, if they're uncorrelated, then x is no help in explaining y in terms of linear regression when x and y are normally distributed. Now remember this, because that's a very important assumption, if x and y are normally distributed. Now, so this line is called the regression line of head circumference on gestational age. This is the line that we eventually want to estimate. And as I said before, up to now we've been doing one parameter. Now we're going to start trying to estimate a line. This is the line where the means of the distributions lie. So this is my attempt at trying to do it coming out of the paper, three-dimensional plot. It's not very great, but there it is. I actually have to thank Nick Cox for drawing this for me. So here's the framework that we're going to be talking about. We are going to be fixing on linearity. So we're going to make the assumption that we're dealing with linearity. That means the regression line is straight. We're going to be assuming homoscedasticity. So remember the homoscedasticity assumption in the analysis of variance? It's the same idea here. That is that this standard deviation of the y's for a given x is constant. So it is 1.6 here. That remains constant. It doesn't matter where we are, which gestational age we're at. And so that is how we're going to do our estimation. If we then want to go on and do some inference with that, we're going to make these two assumptions. One is that we've got a Gaussian data. So for a given x, the head circumference is normally distributed. And we're going to assume independence, our usual assumption of independence. Now, you can relax all these assumptions. Not in this course, though. In this course, we're going to be making these four assumptions. Now, looking at the other, so that was the first idea about the correlation coefficient and relating it to regression. Here's the second. So here is our linear regression. So the mean of the y's for a given x is alpha plus beta x. And we want to make inference about this alpha and this beta. We're going to estimate the intercept and the slope of our regression line. And we're going to assume normality. Then here is the relationship between the slope and the correlation coefficient. In fact, if the standard deviation of the y's is equal to 1 and the standard deviation of the x's is equal to 1, so if we're dealing with standardized variates, if we standardize our variates, then this cancels out and we're left with the slope is the beta. So is equal to rho. The correlation coefficient is the slope of the regression line if we're looking at the standardized variates. So once again, going back to that game on the correlation, so not only can you see how packed they are, how tightly packed they are, so the more tightly packed they are, the higher the rho, but rho is also the slope. So what this is sort of saying is that if the slope is high, then they become closer and closer packed together. If the slope sort of becomes smaller and smaller, the points tend to disaggregate. Putting these two properties, or these two interrelationships between the correlation coefficient and the regression framework together. Okay, so that's the relationship between the two. Now, finally, what we can deduce from all of this is that there's a certain amount of equivalence here. So if we've got normal data, these three hypotheses are going to be equivalent. One, the hypothesis that the correlation coefficient is equal to 0 is going to be totally equivalent to the hypothesis that, and this is the one that we always focus in on, that the slope of the regression line is 0, and that's the same as that the standard deviations are the same. The standard deviation ignoring the covariate x and the standard deviation when you do bring the x into account. These three statements are equivalent. And in fact, if we have normal data, if we're dealing with normal data, if the x's and the y's are normally distributed, this is the same as independence. So here is our assumption, or here is our test for independence. Okay, these are totally equivalent. These three are totally equivalent. And you've seen the equivalence from the framework we've just finished.